welcome. Today we're going to take a look at some ways to work with differential geometry of curves using the Grassmann and Cartan package that I developed. So we'll just get a general idea of some of the things you can do. So let me... So we can define this kind of parameter. We'll make a basic circle. And the Mackie plotting software, sometimes the first time you plot, it takes a few moments, but then it'll work very quickly. So so now we're gonna add the tangent circle to our plot. And this is for visualizing the actual tangent vectors on the circle. So we can see that this is the original circle and these are the tangent vectors pointing to the tangent circle, basically. So this is some of the things we can do, and we can abstract this away to any curve. Doesn't have to be a circle. For example, let's take the parameter from 0 to 2 pi. So this is the unit helix. That's the tangent. And then we can do the arrows of the unit helix as well. Tangent. Oh no, that's arrows 2D. Oh, I guess does that make 2D arrows? Okay. All right. Very nice. So that's how we can visualize these arrows. So those are the tangents on the helix. We can define any kind of curve. For example, the tractrix. This is a curve called the tractrix, which has a cusp here at 0. 1. And that's the tangent curve right there. And what we can do is we can calculate the arc length of the curves. So that's the arc length of this tractrix as a function of t. And yeah, if we want to take a look at the speed, that's the speed of the curve, and at the cusp, the speed is 0 here. So what we can do is we can visualize this tractrix. So this allows us to see what's going on with these tangent vectors on the curve. And let's look at the curvature. So if we look at the curvature, it has a singularity there. So if we want to get a better look at it, we can just bound it to 5, let's say. And then we can have this cutoff here at 5. And then we can better see how the curvature approaches this cutoff. And the alternative to this is to use the radius. The radius now is a finite value at 0 here. So this is alternative way of taking a look at this. Now, if we take a look at the graph of the tractrix, we get a three-dimensional curve. And now we add the tangent curve as well. And we'll add the arrows. So this is just another way of taking a look and seeing how how these tangent vectors can be visualized on a curve like this. There's, you know, a bunch of more functions available. We can also visualize, particularly for the track tricks, we can plot the evolute. And the if we define evolute of f minus f, we can get these, basically these arrows. And now we can get a better understanding of how the track tricks is related to the evolute of itself, using basically these arrows here. And the inverse of this is called the involute. And yeah, you can basically start with so this is basically the hyperbolic cosine of t. This is what we start with. Similarly, we can basically obtain from this hyperbolic cosine the involute, which is then the same as the track tricks. There you go. And then we can again do the arrows 2D. And then those are the arrows. So we did both of those things. And another thing you can do is you can take the tangent angle of a curve. So that's for a unit circle, but you can do the same thing for different functions. Total curvature. Two pi for the unit circle. Just to kind of give an approximate result. This is an approximation of a unit circle, of course. It's not, doesn't have an infinite number of points. But similarly, you can calculate the winding number. Approximately 1. And some of the other interesting functions are the ability to make a plane curve from a curvature. Here's one of the more interesting examples you can make. So yeah, it's lots of nice things you can do. Let's go back to the helix. Some of the other things you can do is you can visualize this osculating plane. And let's add the arrows. So this is what the osculating plane looks like along the helix. Let's try it again. Let's try arrows 2D. Yeah, so you can use different arrow types here, you know. And you can also visualize the binormal here. So now you can see that there's a binormal vector sticking out of the plane here. This is basically the vector that's perpendicular to this osculating plane. So yeah, there's many different methods and functionalities built in to work with curves. There's even more, you know. I can't even mention them all in this one video because it's gonna be too long of a video. But there's many more functionalities for curves available as well. One more that I'll mention is the one for the Wronskian. So you can ask for the Wronskian, for example, the cosine and the sine, which is 1. So that's a nice convenient function, the Wronskian. I don't know, I'm just someone who's who always likes, you know, having many different kinds of functions available to work with curves and differential geometry and so on. So this is some of the functionality that I developed, and if you're interested in this, there's more information about it. There's this and a lot more information included in my new textbook. It's my first book that I published. It's called Principal Differential Geometric Algebra. So if you're interested in this kind of differential geometry of curves and many other topics, you can check out my book. Principal Differential Geometric Algebra. Compute using Grassmann.jl and Cartan.jl is my new book. It's the first book I've written and published, and it's about the programming language things I've been working on. And there's a hardcover and a paperback version. It's 500 pages, with over 500 pages with many different scientifically reproducible diagrams and calculations, introducing people to the programming language paradigm that I've been working with, which is differential geometric algebra, and also some category theory at the beginning here. So yeah, this is a great textbook, new one that I've published. It's the hardcover version here. Got the back side here. So can read the back side here. Principal Differential Geometric Algebra is the first reference of its kind, built on rigorous category theory foundations and a full unified TensorField computational language design for differential geometry. This category theory foundation presented is a custom-designed formalism for categories to specifically emphasize the existence of choice morphisms, relevant to mathematicians interested in how the axiom of choice appears in class and set theory. Next, the book introduces essentials of geometric algebra as the primary basis for differential geometric algebra computational language design using Grassmann.jl library for the Julia language. Developed completely from scratch, Grassmann.jl introduced many pioneering computational language designs to enable reproducible scientific research with numerical differential geometric algebra. Building on Grassmann.jl, the Cartan package is the first computational language design to pioneer a FrameBundle for the PrincipalFiber G-bundle formalism used in advanced differential geometry. Not only does Cartan.jl present completely new programming paradigms for working with an abstract FiberBundle topology using numerical analysis, it also unifies the topological implementations of structured and unstructured finite element methods and also spectral element methods. This book emphasizes the analysis of eigen-characteristics with multilinear algebra, differential geometry, and partial differential equations. Many figures and diagrams are included, all scientifically reproducible with concise programming language. Partial differential equation examples are evaluated with boundary conditions found in the literature to help scientists and engineers validate the usefulness of the computational language design. Also included are many special and elliptic functions and appendices for basics of the Julia language, the Reduce.jl package, the Fatou.jl package, and also the new Unified System of Quantities for physics units from the UnitSystems.jl package. So this is the first edition from 2025 of my textbook, Principal Differential Geometric Algebra, compute using Grassmann.jl, Cartan.jl. So I'm excited about this new textbook. It's now available. Yes, so includes very much interesting information about differential geometry, partial differential equations, geometric algebra. Some category theory as well. So, yeah, I'd be interested to, get people's feedback about this. This is my first book. So, yeah, and if you buy this book, that helps fund my research project in the math and programming language design. So thank you very much for checking it out. It's my new textbook. Yeah, covers many different topics. Yeah, thank you for checking it out.
parallel is 0. So there's no force on a field-aligned current. So the superimposition of the circular component with the linear component, or an arbitrary angle of input of current, is, of course, circle plus straight lines healing. Now, why they form in pairs is not an easy question. They do. That's a laboratory finding. The little curve on the right just shows that if these things get too far apart, there seems to be a force to pull them back together. If they get too close together, there's a force that pushes them apart.